So I'm going to start by just introducing myself a little bit. I've spent most of the last 35 years in and around the aerospace and defense industry. And while in the industry, I was a researcher, a system engineer, a program manager, and a business innovator. I worked for Honeywell, L'Oreal, and Lockheed Martin, mainly in the areas of surface-to-air missile countermeasures and ultrasonic imaging. And after joining Mentor Graphics, which later became Siemens, I served the industry by marketing and selling development software to market leaders like Boeing, Northrop Grumman, and Honeywell. So today, I have the privilege of representing Siemens' Integrated Electrical Systems business segment as we apply digital technology to accelerate our customers' business processes. I will now let my colleague, Steve Caravella, introduce himself.
Hello, everyone. This is Steve Caravella. Earlier this year, I joined Siemens Integrated Electrical Systems, working with Anthony to focus on the aerospace and defense industry. I started my career at Boeing, where I worked on commercial aircraft, specifically wide bodies, and later moved to Gulfstream Aerospace, where I've spent many years working on business jets. I've been fortunate to work in the manufacturing sector in a variety of engineering roles, ranging from design, project engineering, program management, and this has given me a broad exposure to not just engineering design, but to certification and a lot of interaction with manufacturing. I've done this in the settings of new product development, outfitting of aircraft, modification of in-service aircraft, and service support. So I'm pleased to be here to talk about the challenges the industry faces today in the area of harness manufacturing. So thank you for joining us.
Thank you, Steve. So let's get into it. So aerospace harness suppliers are under increasing pressure, and whether they're within an OEM or acting as an independent supplier, these manufacturing teams are under more stress than ever. They find their business suffering from profitability constraints on all sides, from increased harness complexity driven by more electric platforms to the need to rapidly transition design changes into production, to serving demanding customers who expect ever lower cost assemblies delivered just in time, while they threaten to further vertically integrate into harness manufacture. Meanwhile, platform designers are changing their electrical systems and consequently their harnesses ever more frequently to respond to the changing demands of their customers. They expect their harness suppliers to keep up, transitioning these changes into production quickly and with a minimum of cost and schedule impact. These trends in the industry make it ever more difficult for harness manufacturers to meet expectations for responsiveness, quality, delivery time, and profitability. So another quick question for you all. Of these 8 trends, which do you see impacting your businesses? You can choose one or more if you feel that it's impacting you. Okay, let's see. Looks like the winner is increased margin pressure from customers. And that is not unexpected. We hear that a lot, especially with the OEMs pushing back on asking their suppliers to participate more in helping them increase their own margins. So thank you very much for sharing. So what we find is that OEMs need to differentiate their platforms and address the more demanding missions they face, and that this requires new platform capabilities. Whether it's getting a commercial aircraft to fly 8,000 miles point to point, or enabling a modern fighter to work in tandem with a drone squadron, most of these capabilities are implemented electrically. Furthermore, the unending pursuit of higher reliability and lower aircraft weight has driven platform designers to move toward hybrid systems, electromechanical, electrohydraulic, electropneumatic. You can see both of these trends depicted in this military aircraft example. This has led to a vast increase in the number and extent of electrical systems on aircraft. We can see just how much by examining the amount of power generated on a modern aircraft. While electrical power generation has been increasing throughout the history of aviation, over the last 50 years, it's increased by a factor of 10. Most of that has arrived with what is known as the more electric aircraft. For example, Boeing 787 can now produce about a megawatt of electrical power. That means that on a 19-hour flight from New York to Singapore, the 787 produces enough power, or could produce enough power, to supply 21 American homes for a month. That's a lot of power. This increase in reliance on electrical systems has had a consequent impact on the complexity of the electrical distribution system, or EWIS. Today, it's not unusual for modern aircraft to support electrical systems with more than 500 kilometers in total cable length, up to 100,000 wires, and more than 40,000 connectors. The electrical wiring system now represents a significant weight driver, comprising about 3% of total aircraft weight. It can exceed 7,000 kilograms on some aircraft. This relatively new reliance on electrical systems has substantially increased the risk our programs face, especially as they transition to production. Current processes were developed for a world where most of the functionality was implemented mechanically, including pneumatics and hydraulics. As an industry, we know how to work around late-breaking problems in these disciplines without major program iterations. Now, with electrical front and center in new capability implementation, and this includes networks and software, there is a lot more at stake. A problem discovered in the first article integration or transition to production can mean a major development cycle, potentially costing billions of unexpected dollars. This not only puts a program at risk, its cost and schedule, but also the reputations of the program team, the reputation of the business unit, and in the worst case, the viability of the company itself. At the same time, platform OEMs are requesting more changes to implement the EWIS than ever before. First, they must increasingly respond to their customers' needs for bespoke platform configurations. They not only must answer these demands from their customers, but they are also using responsiveness as a way to differentiate themselves and gain competitive advantage. Next, regulatory flight certification is becoming more and more stringent. Not only are they changing, not only are the regulations changing in response to new incidents, but the ability to avoid their application through grandfathering of new aircraft variants has disappeared. Finally, OEMs and suppliers must integrate changes arising from electrical system design improvements for cost reduction, manufacturability, reliability, and performance. Together, these vectors of change stress harness manufacturers, whether they are vertically integrated teams within the OEMs or external Tier 1 suppliers. They need to respond to change from both the OEMs and their own harness product and process engineering teams. And they must do this urgently, as electrical system changes are frequently communicated at the last minute, with little time to spare if a production program is to meet its schedule. All this results in a new harness manufacturing reality, more harness variants produced in more frequent, shorter duration production runs, and in smaller quantities. So Steve's going to examine what this can mean for achieving profitability.
Okay, thanks, Anthony. So I wanted to talk a little bit in the context of what Anthony was talking about, of one of the challenges, and this is really, when you look at your ramp up of production, as well as incorporating changes. So if you look at the chart here, we've got an efficiency level on the left and a period of time. So typically, we'll sit down, a manufacturer will sit down and come up with a ramp up plan, and it'll start ahead of having to achieve full rate production, which is represented as the SOP here, start of production. So this probably looks real familiar to everybody. It's typical learning curve and a ramp up. The reality, though, where the challenge comes in is we're trying to get to our profit level at the 80% point. However, when we implement this, things can happen, right? So if a harness is complex, humans are planning this process, therefore mistakes get made. It could be in the tooling, it could be in work instructions or any of the other production's artifacts. So what actually happens is this sort of sawtooth of progress and a little bit of backstepping as issues get found and have to be resolved. Of course, while we're addressing the issues, time continues to move, and eventually we find ourselves at the point where we're ready to start, or the date we set for starting full production, but we're below our target efficiency. So in this case, our target was 80%, and let's say we're at 67%. Now, on the surface, that doesn't necessarily sound so bad because we've been making progress, working through issues. But the real problem is that by the time we actually get up to 80%, which is further in time, we've lost money on harnesses. We've lost money, we've lost time, we may have late deliveries. So that area shaded in red is really the result of the challenges we realize in practice. Eventually we get to 80%, but at that point we may actually have lost our entire profit for our production run for that. And when you combine that with the frequent and shorter production durations, this really is a recipe for disaster from a margin standpoint for our organization. So Tony's going to talk a little bit about some of the things that can be done to improve this situation.
Yeah, and before I get there, though, I am going to mention that this situation is actually even worse than Steve mentioned, because our ability to avoid and recover from these mistakes is being hampered as we lose our best people to retirement. I won't spend a lot of time on this, but suffice to say, a generational demographic shift is underway in our workforce right now, and our largest, most skilled employee cohort, the baby boom, is retiring. And as they leave all our organizations, not the manufacturing ones, the expertise and tribal knowledge we've relied upon to proactively avoid error and work around it is leaving too. And this means that it is even harder for our teams to deal with the challenges presented by the demands of modern harness manufacture. Finally, the tools used by most harness manufacturers today don't make their task any easier. Generally, the state-of-the-art for manufacturing engineering employs manual processes and slow and disconnected tool sets. These processes are time-consuming and expensive. They often miss or even introduce errors into manufacturing tooling and work instructions, leaving issues to be found late in the game, even after the manufacturing cycle has begun. This forces expensive design iterations and process changes. So what are we to do? Well, the most sophisticated members of the manufacturing community recognize the need to change. Using a technique termed digitalization, they are applying digital technology to transform their business processes. They are already adopting model-based development techniques from concept development through design into manufacturing to reduce cost and schedule risk, accelerate production ramp, and improve productivity. As shown here, leaders in the United States Department of Defense endorsed this shift to a digitally connected design and manufacturing ecosystem. And for those forward-acting companies, the benefits are already paying off. Take the case of the Boeing Saab T-7A trainer program. By using model-based development techniques, they were able to go from platform concept to first flight in under 3 years. As Boeing's chief engineer, Paul Newell, stated, "We are competing against proven, in-production aircraft, so we had to do things differently." The result, by applying model-based development techniques, the Boeing Saab team was able to build their confidence to the point where they could bid $10 billion below the U.S. Air Force's expected lifecycle program cost. This won the program for them. In companies like these, program design teams build a configuration-controlled digital twin or model of the platform's electrical system. The manufacturing engineering team uses this electrical digital twin to develop its own digital twin of harness production. They use this to design, plan, and optimize the overall production process. Electrical and electronic systems development platforms like Siemens Capital are architected to ensure digital data continuity is maintained as the program proceeds from phase to phase. They do this using an underlying digital thread. This ensures that information added to the electrical system and harness production models is accurately and contemporaneously presented to the manufacturing, engineering, and design teams. In this way, both teams work from an authoritative description of the electrical system and are informed of relevant improvements and corrections made by the others. While Capital has always been a model-based approach to electrical distribution system development, it has recently expanded to support electrical system modeling, electrical system architecture design and optimization, and software network development. These two are fully integrated across the product lifecycle and make use of assistance from many of Siemens' market-leading solutions. Capital consumes information from a variety of requirements and system modeling environments. It normalizes this information to feed the platform electrical system development process. This begins with the capture of an electrical and electronic system functional model. This functional model not only incorporates all the tasks and roles expected of the electrical system, it also accounts for all communication between these functions and maps the relevant system's requirements to them. These are important features of the model to get right early in the electrical system development process, since by virtue of the digital thread, these relationships will be preserved throughout the platform lifecycle, including during the transition to harness manufacturing. This enables electrical systems engineers to design and optimize electrical system architecture. They explore architectural options to better understand the impact of trade-offs early in the development lifecycle and are empowered to pick a better starting point for all the effort that follows. This means fewer unanticipated changes at the architectural level that ripple down through the electrical systems design and ultimately result in change to harness production configuration. Armed with the chosen architecture, Capital extracts the information necessary to implement the electrical system. It intelligently parses this information to feed lifecycle development in 4 separate but related electrical disciplines: electrical distribution, or EWIS, electronics, communication networks, and software. Each discipline uses this data across the complete development lifecycle from design through production and finally into operational maintenance. Capital's digital thread not only connects these related electrical disciplines, it also extends to the mechanical discipline and to the platform's product lifecycle and application lifecycle management environments. This allows electrical and mechanical co-design, platform-level configuration control and revision control, and the capability to configure the platform across domains and up and down the product development lifecycle. Today, we focus on the harness domain within the electrical system and harness development flow. Steve's now going to introduce us to the digital thread and flow that actually serves this domain specifically.
Thank you. The tools and processes that comprise the harness domain represent an advanced solution unto themselves. The overall flow ranges from harness design and costing to work instruction generation. It encompasses product engineering, including product cost optimization, form board design, assembly and subassembly design, manufacturing process design, optimization, and documentation. As was mentioned earlier, the tools directly access the electrical system digital twin to enable an automated harness manufacturing engineering flow that requires no manual data entry. As a result, generating important manufacturing aids, tooling, and even cost estimates is seamless and becomes second nature. 2 items to note in this flow are the capability to do line balancing of assembly tasks for smart resource utilization and the capability to do process simulation to validate and optimize the process. The tools enable better retention of institutional knowledge as well. So every company has its rules and production process models, and these tools capture that, as well as provide the capability to validate the harness models early in the process. With this information, the bill of process can be generated automatically, resulting in the outputs needed to supply information to downstream customers. Feedback can be gathered from the various users and incorporated into the upstream inputs, with the automation also providing an efficient way of supporting continuous change and improvement back into the outputs. I'm going to take a moment and talk about two capabilities specific to form board design that I'd like to highlight that can provide substantial benefit to a harness manufacturer. The first one addresses the need to reduce tooling costs, optimize factory space, and storage of form boards. So here we see two form boards for harnesses that look relatively similar, but they have several different branches and terminations. So maybe they're similar with about 30% differences. Now typically, this would mean generating two different form boards that need to be managed, they need to be built, stored, and take floor space. If we merge these form boards into a single form board, we can produce either harness on this form board. You can see the differences highlighted in either blue or yellow to make either harness. And this will reduce the number of form boards that need to be created and managed. Getting some noise on the line here. I'm not sure where it's coming from. The second capability I would like to highlight is the assistance the tool provides to create ergonomic form board designs and improve efficiency. So in this animation, we'll walk through how a form board is made. So when starting, the harness is brought in and flattened, and it will need to be arranged. So starting with the main trunk, the harness is positioned onto the board into an optimum work zone. As you can see, you can turn on some color shading here. So we want to maximize what is in the green area, which is the most accessible space. So you can position the different branches by grabbing the grip points, stretching them, locating them. One thing you'll notice is that in the bends, the system knows what the minimum bend radius is for each of the bundles and maintains that. And as we move this around, you can zoom in, you can see how we're bringing everything closer to the center, providing good space. I'll let this go a little bit longer because one of the other benefits that this tool provides is there's an Insight tab on here where it can actually keep track of how much of the harness fabrication steps are within the green, yellow, and red zones. We'll get to that in a second. So now we'll look at the Insight tab. And it actually will show you, as we move things closer to the center, the quantity of work that's falling in each of the spaces. So what benefits have companies realized from using these tools? So here I've highlighted in white some of the manufacturing advantages gained from applying capital in harness manufacturing. There's one in particular I'd like to discuss. It's near the bottom. It's called First Time Right Harness Achieved. So in this case, a customer using capital, integrated with their MCAD tool, designed the complete and full harness assemblies and fabricated them to their final configuration with the goal of not having to terminate any of the harnesses on board the platform at the time of installation. So when installation was done, they were able to fit all the harnesses with no rework, saving many hours of installation time. Specifically, it's for a space capsule, so that's small spaces and really frees up the area for other people to do their work. So this is a clear example of how model-based development can impact favorably harness manufacturing to allow a lot of the work to be done in the back shops and avoid reduce installation time. So I'm going to come back to this chart I showed earlier, looking at production ramp-up. So this is what we saw before, and I think everybody can agree that if we use better tools in the design process, we can improve upon our plan. So we front-load the activities. We have, vetted libraries. We have DRCs, which are design rule checks, and we've got validation capability in the tools. So we would expect the ramp-up to improve, like so. However, this is really sort of a small gain compared to what we will see in actuality. So the tool brings into it the ability to simulate, analyze, optimize, and validate the manufacturing process. So what we can expect to actually achieve is a similar sawtooth effect as we work through the challenges that come with any ramp up. But as you can see, it's much closer to the planned ramp line with a lot less extreme variations because we've had the capability to simulate and work out kinks before we actually started into production. So Anthony is going to wrap this up here by discussing what this means for your business.
Yeah, and what I want to emphasize is that the power of this environment is the access to the digital twin of the electrical system throughout the product lifecycle. By harness manufacturers having access to that information directly, they can automate and reduce the errors associated with the entire set of artifacts required in order to move through their manufacturing process. And companies that are applying these model-based techniques today are realizing quantitative business and operational benefits. You can see that the value of taking action to digitalize business processes is substantial. In a recent study, the OECD found that companies who took the initiative to digitalize, as we described, have increased productivity by as much as 25% and propelled themselves into the top 5% of their industry's financial performance cohort. So thank you for joining today. In summary, a model-based harness manufacturing engineering solution contributes to retaining and even improving your reputation for predictable harness manufacture. Using a comprehensive electrical and electronic systems development portfolio provides harness manufacturing engineers direct access to the configuration control digital twin of the platform's electrical system. And this accelerates manufacturing engineering, reduces errors, and enables manufacturers to respond dexterously in the face of change. The result is higher productivity, less scrap, and ultimately greater profitability.